So now we look at interacting flow paths. A shared completeness path linking oscillations can do a great deal more than just link oscillations as long as it remains a shared completeness path linking oscillations. So up here we have two paths flowing into a combinational circuit that flows into a single flow that flows out into another flow path. And here we have the link, the enable link, and the completeness. And ahead of that we have a combinational circuit. And this combinational circuit fulfills the completeness criterion, which means that whenever its output is transitions to data, it means that both inputs have transitioned to data. And whenever its output transitions to null, it means that both inputs have transitioned to null. So this circuit fulfills the completeness criterion in the same way that the link circuit fulfilled the completeness criterion. And these two circuits together, the combinational circuit and the link circuit, together form a single shared completeness path linking the two input oscillations of the two input flow paths and the oscillation of the output flow path. So let's look at this in some more detail now. Okay, we'll specify a path interaction with a table that specifies the output rail for all combinations of input rails. Here we have a path named trinary with 3 rails, a path named binary with 2 rails, and a path named quaternary with 4 rails, 0, 1, 2, and 3. We'll map this table directly in to a set of equations, one equation for each output rail. This is quaternary 0, quaternary 1, 2, and 3. And we'll see here that quaternary 0 occurs when trinary is 0 and binary is 0. So here we have binary 0 and trinary 0 flows to quaternary 0. Now these equations are all going to be and/or equations. They map directly off the table, and it's this and this, or this and this, or this and this. So it's and/or equations. Now we'll represent these and/or equations as functional syntax, functional relations, rather than infix relations, because it's going to turn out that our symbolic specification is going to be a large, complex interweaving of and/or relations of different contexts. So we'll use the functional notation, and we'll, instead of saying and or all the time, we'll use syntax to specify and or. So an OR relation is encompassed in curly braces, and an AND relation is encompassed in brackets. So this is binary 0 and trinary 0. This is trinary 0 and binary 1, or trinary 1 and binary 0. So the two AND relations are encompassed in the curly braces, which makes them OR related. So that's quaternary 1. So we have our 4 equations mapped directly from the table. Next, we want to specify the component. So we'll specify the tokens. Trinary is 3 rails, binary 0, 1, quaternary named through 4 rails named 0, 1, 2, and 3. And this is our component specification. Trinary, binary flows to quaternary. Now, the flow relation will specify a bit more about this flow, and it specifies specifically that trinary and binary, enclosed in brackets, flow to quaternary. In other words, it requires both of them to create the quaternary. Okay, so the body of the component now becomes our equations. So this is the same 4 equations. And the closure, we close trinary with the completeness of quaternary, we close binary with the completeness of quaternary, and that's the end of our component specification, and then we sync quaternary. It's not going anywhere, we're just going to look at it in the waveforms. Okay, so now we set up the test bench for this with 2 ring generators, a 3-rail ring generator and a 2-rail ring generator. And those will generate successive rails. So the 2-rail generator will generate 0, 1, 0, 1, 0, 1, and that will feed binary. And the 3-rail generator will generate 0, 1, 2, 0, 1, 2, and that will feed trinary. And that's the input to our component. and then that'll generate the quaternary. So now, as these two rings generate their sequences, it'll be 0, 1, 0, 1, 0, 1, 0, 1, 2, 0, 1, 2. So this will generate all the possible input patterns, and these are the quaternary results for the input patterns. So the quaternary will be 0, 2, 2, 1, 1, 3. So this is quat, the output. In the waveform viewer, this is 0, this is 3. So you can see that we have 0, 2, 2, 1, 1, 3, 0, 2, 2, 1, 1, 3. So our set of and/or equations maps directly into an NCL minterm and/or circuit. And we call this the canonical minterm form because firstly, the equations map directly into this form of circuit. And secondly, from this minterm form of circuit, we can see by inspection that the circuit fulfills the completeness criterion. And the completeness criterion states that when an output transitions to data, when one rail transitions to data, it implies that the input is completely transitioned to data, that data wavefront has flowed completely through the circuit, and that's the correct resolution of the presented input. So you can see if one rail of trinary transitions to data and one rail of binary transitions to data, only one of these gates will transition to data, and that transition will propagate through the circuit to the output, fulfilling the completeness criterion. And the completeness criterion works for the null also. So when this rail that was data becomes null, it implies that the input is completely transitioned to null, and the null wavefront is flowed completely through the circuit, and that the transition to null of the output is the correct resolution of the presented input, which is now all null. So the completeness criterion works in both directions for the transition to data and the transition to null. This is the Verilog program that implements this circuit. This is the rank of 2 of 2 gates, that is the minterm. This is the 2 OR gates, the 1 of 2s. This is the inversion of the completeness to create the enable, the inversion here. And this is the rank of 2 of 2 gates forming the enable rank of the link. And this is the completeness, the 1 of 4 forming the completeness of the link. Now this minterm circuit is identical to DIMS, delay insensitive minterm synthesis, which was developed 25 years ago by Sparso, Stanstrup, and Sorensen. And they developed it in terms of C elements and OR gates. Now, threshold 2 is identical to a C element, and the threshold 1 is identical to an OR gate. But their difficulty was that in thinking of this in terms of C elements and OR gates, they couldn't optimize this structure, and this is not the optimal structure to implement the function with. But with NCL, we can optimize this structure. So it turns out we can optimize the combinational logic into the enable rank of a link, but not past the enable rank into the completeness logic. And to represent that symbolically, we will AND the quad enable into each of the equations, integrating the enable rank into the equations themselves. Now we can optimize these equations simply by refactoring the equations. So we can factor the terms of the equations into 4 input or fewer terms of and/or relations. And any and/or relation of 4 or fewer inputs will map to a gate in the NCL library. That's the whole point of the library. Okay, so that's what we're doing here. We're factoring the equations, mapping them into gates from the library, and that is our NCL circuit. And for each circuit, we have the Verilog program that implements that circuit. So this is optimization A, and the Verilog circuit is bitrack quat A.V. So this is optimization B. It's just another factoring of the equations and another mapping into gates in the library. This is the Verilog program that implements it. And this is optimization B. This is optimization C. It's yet another factoring of the equations into gates in the library. And this is the Verilog program that implements it. So now we have 4 different versions of the logic circuits mapped from the single set of specification equations. Now, up here we have a little table that gives us, compares the versions. We have the minterm, the A, B, and C optimization. So we see that B has the fewest number of gates. It also has the fewest number of transitions on average and the shortest delay through the circuit on average. So in this case might be the optimal circuit. Now all 4 circuits were mapped from the same set of specification equations. The equations were not modified in any sense, and all 4 circuits were a complete mapping. And we know that the set of equations fulfills the completeness criterion. So all 4 circuits fulfill the completeness criterion. So each of the 4 circuits is a shared completeness behavior linking 3 oscillations and performing a path interaction function.